Night settles unevenly over southeastern Australia. At altitude, the air is colder than expected for the season. Thin layers of cloud drift across the flight path, barely visible from the ground but dense enough to distort the horizon from the cockpit. There is no storm, no towering cumulonimbus, just a quiet, persistent haze, subtle, almost unremarkable. At 19,000 feet, a Vickers Viscount 720 moves steadily through the darkness. Its four turboprop engines maintain a consistent rhythm, measured, reliable. The Viscount had built its reputation on this sound. Smooth, predictable, a modern aircraft for a rapidly modernizing country. On this route, between Sydney and Melbourne, it represents routine, familiarity. Inside the cabin, the atmosphere is calm. Passengers sit in the dim glow of overhead lighting. Some are reading, others are asleep. The flight is not unusual. It has been flown countless times before. In the cockpit, instrumentation casts a muted green light across the panels. The layout is orderly, engine gauges aligned, flight instruments centered, controls within easy reach. The aircraft is stable. For now, there is no sudden event, no warning that stands out, only a gradual shift, almost imperceptible at first, a slight deviation. The artificial horizon begins to suggest a change so small it could be dismissed, a minor roll, something that could be attributed to light turbulence, the kind that requires no correction, the kind pilots are trained to ignore unless it develops. But it does not return to neutral. The aircraft continues, subtly, to move away from level flight. The control inputs are minimal. Routine corrections, small adjustments to maintain attitude. Nothing aggressive, nothing urgent. The kind of inputs made almost unconsciously. Yet the response is not entirely consistent. There's a delay, a softness in the controls, not a failure. Not yet, just a difference. Outside, the night offers no visual reference. The cloud layer removes any sense of horizon. There are no city lights below, no coastline, no stars clearly visible through the thin overcast. The aircraft is now fully dependent on its instruments. Inside the cockpit, that dependency is absolute. Another slight deviation appears, this time in pitch. The nose angle changes marginally. Engine power remains constant. There is no immediate reason for concern, but the aircraft is no longer holding its previous stability. Corrections follow. Again, small. Again, measured. But the aircraft does not fully comply. The motion becomes less predictable. A gentle oscillation begins to form. Not violent, not alarming, but noticeable. A pattern that does not belong to normal cruise conditions. It is the kind of movement that prompts attention, but not alarm. Not yet. Seconds pass. Then more. The oscillation tightens. Roll becomes more pronounced. Pitch begins to follow. The aircraft is no longer simply drifting. It is beginning to move with intent, but not by design. Engine noise remains unchanged. There is no explosion, no mechanical brake audible within the cabin. Everything sounds normal, but the motion is not. Instruments now demand closer scrutiny. One reading suggests a bank angle increasing beyond what was commanded. Another indicates a rate of descent that does not match engine output. The discrepancy is subtle, but real. The aircraft is entering a state where interpretation matters more than reaction. And interpretation is becoming more difficult. Without an external horizon, the instruments are the only truth available. But when indications begin to diverge, even slightly, the burden shifts to the crew to determine which signals to trust. This is where routine begins to erode. The Viscount continues forward, but its path is no longer stable. The oscillation sharpens. Control inputs increase, slightly more assertive now, still controlled, still professional, but no longer casual. The aircraft responds, but not completely. There is resistance, a growing disconnect between input and outcome. The nose drops further. Altitude begins to decay, slowly at first, then with increasing consistency. The descent is no longer incidental. It is developing. Inside the cabin, the change is felt before it is understood. A shift in weight, a subtle forward pull, the kind that causes passengers to pause, briefly, before returning to what they were doing. No announcements are made. There is no panic, only a quiet, shared awareness that something has changed. In the cockpit, the situation is narrowing. Options begin to compress. The aircraft's attitude continues to diverge from expected behavior. Roll increases. Pitch fluctuates. Descent rate builds. And still, there is no single, identifiable failure. Only a system that is no longer behaving as a system should. The Viscount is now moving through cloud with increasing speed in descent. The margin for recovery is shrinking. Altitude, once abundant, is now a factor. Every second matters more than the last. The aircraft banks further. Not sharply, but enough. Enough to require decisive correction. Control inputs increase again, but the response is uneven. There is a point, difficult to define precisely, where a manageable situation becomes something else. This is that point. The aircraft is no longer in stable flight. It is no longer fully under control, and yet it has not entered chaos. Not completely. There is still structure, still continuity, but it is fragile, and it is breaking down. The descent steepens. Cloud layers pass more quickly now. The aircraft is accelerating, not through added power, but through loss of altitude. The engines continue their steady output, unchanged, almost indifferent. Inside the cockpit, the instruments continue to display information. But information alone is no longer enough. Interpretation has become the critical factor, and time is running out. The Viscount continues downward into the darkness. No external reference, no visual recovery, only instruments, only decisions, only seconds. What began as a routine flight has entered a phase from which recovery is no longer certain. The aircraft disappears deeper into cloud, and the night closes in around it. In the early 1960s, Australia's aviation network was entering a period of quiet transformation. Distances that once defined the continent were beginning to lose their meaning. Routes between major cities, Sydney, Melbourne, Brisbane, Adelaide, were no longer logistical challenges. They were routines. Timetables tightened. Frequencies increased. Aircraft departed and arrived with growing regularity. At the center of this shift was Trans-Australia Airlines. Established to provide a reliable national carrier, Trans-Australia Airlines, often known simply as TA, had built its identity on consistency. It was not marketed as luxurious. It was not experimental. It was dependable. Flights departed on time. Aircraft were maintained to strict standards. Crews were trained within a system that emphasized discipline over improvisation. On the Sydney-Melbourne route, this reliability was especially visible. It was one of the busiest air corridors in the country. Business travelers, government officials, and private passengers moved between the two cities daily. The journey, once measured in long hours by rail or road, had been reduced to a matter of routine scheduling. Aircraft like the Vickers Viscount 720 made that routine possible. The aircraft era, introduced in the 1950s, the Viscount represented a significant advancement in commercial aviation. It was among the first turboprop airliners to achieve widespread success. Compared to earlier piston-engine aircraft, it offered smoother flight characteristics, reduced vibration, and improved passenger comfort. Its four Rolls-Royce Dart engines provided steady, reliable power. The aircraft cruised efficiently at medium altitudes, typically between 15,000 and 25,000 feet, where weather conditions were often manageable and fuel consumption remained economical. For passengers, the difference was noticeable. Cabins were quieter, windows were larger, flights felt more stable. For operators like TAA, the Viscount offered something equally valuable: predictability. It was not the fastest aircraft in the sky, but it was consistent. Its systems were well understood. Maintenance procedures were established. Performance envelopes were clearly defined. In an aviation environment still evolving, those qualities mattered more than speed. The route. The Sydney-Melbourne corridor was more than just a connection between two cities. It was a test of operational efficiency. Flights followed established airways, guided by radio navigation beacons rather than satellite systems, which did not yet exist. Pilots relied on a combination of ground-based signals, onboard instruments, and procedural discipline. Weather along the route could vary. Coastal systems moved inland unpredictably. Low cloud layers were common. Visibility could change quickly, particularly at night. While severe storms were not constant, the environment required attention. Still, these were known variables. They were part of routine operations. Nothing about the route suggested unusual risk. Aviation standards of the time. By modern standards, aviation in the early 1960s operated with limitations that were accepted as normal. Cockpit instrumentation, while advanced for its time, lacked redundancy in certain areas. Systems that would later be duplicated or automated were, at the time, singular and manually interpreted. Flight data recorders were not yet mandatory. Cockpit voice recorders did not exist in commercial service. When an incident occurred, investigators relied heavily on physical evidence, maintenance records, and operational reconstruction. There were no digital traces to review, no recorded conversations to analyze. Safety, therefore, was built not only on technology, but on procedure. Pilots were trained to manage aircraft through disciplined adherence to instruments. In conditions where visual reference was lost, such as night flight through cloud, instrument flying became absolute. This required precision. It also required trust. Trust that the instruments were accurate. Trust that the aircraft would respond as expected. Trust that the system, as a whole, would behave predictably. The crew culture. Aircrew training in this era emphasized hierarchy and procedural correctness. Captains were authority figures. First officers supported decision-making but were not expected to challenge it unless absolutely necessary. Crew resource management, now a standard concept, had not yet been formalized. This did not imply a lack of competence. On the contrary, pilots were highly skilled. They were trained to handle complex situations with limited tools. But the structure of cockpit interaction was different from modern standards. Decisions were centralized. Interpretations were often individual. In situations where ambiguity arose, particularly involving instrument readings, the resolution depended heavily on the captain's judgment. Routine without warning. On the day of the flight, there was no indication that anything would deviate from expectation. The aircraft had completed previous sectors without incident. Maintenance records did not suggest any critical unresolved issues. Weather reports indicated manageable conditions along the route. Cloud layers were present, but not severe. There were no major storm systems forecast to interfere with normal operations. Passengers boarded as they had on countless flights before. Crew prepared the aircraft according to standard procedure. Checklists were completed. Systems were verified. Clearance was received. Departure followed routine timing. From every measurable perspective, this was an ordinary flight, and that is what defined it. There was no singular warning, no clear signal that this flight would become different from the thousands that preceded it. The aircraft entered the airspace between Sydney and Melbourne as part of a system that functioned day after day with quiet reliability. But within that system, certain vulnerabilities remained. They were not obvious. They were not frequently encountered, but they existed. In the interaction between aircraft design, environmental conditions, and human interpretation, there were edges, points where clarity could give way to uncertainty, points where small deviations, if unrecognized, could begin to compound. The Viscount moved steadily along its route, guided by procedures that had proven effective over time. Yet those procedures depended on assumptions that instruments reflected reality, that aircraft responses matched inputs, that environmental factors remained within predictable bounds. When those assumptions held, the system worked. When they did not, the margin for correction narrowed quickly. On this flight, somewhere between departure and destination, those margins began to shift, not abruptly, not dramatically, but enough to begin a sequence that would not be immediately visible, enough to place the aircraft, and those within it, on a path that would only become clear in retrospect. Understanding the final moments of the flight requires stepping away from the timeline, not forward, not backward, but outward. The accident did not emerge from a single point of failure. It developed within a system, an interaction of design, human interpretation, and environment. Each element, on its own, was manageable. Together, under specific conditions, they created something less stable. This is where the structure begins to take shape. Aircraft, design and limitations. The Vickers Viscount 720 was, by most measures, a reliable aircraft. Its turboprop configuration provided smoother operation than earlier piston-driven airliners. The Rolls-Royce Dart engines were well regarded for their durability. The aircraft's pressurized cabin allowed it to cruise above much of the lower-level weather, improving both efficiency and comfort. Aerodynamically, the Viscount was stable. It was designed to resist abrupt changes in attitude. Control inputs translated into predictable responses under normal conditions. The aircraft was not prone to sudden instability without cause. But stable did not mean immune. Like all aircraft of its generation, the Viscount had limitations, particularly in the way it communicated those limits to the crew. Its flight instruments relied on mechanical and gyroscopic systems. These were precise, but not infallible. Under certain conditions, especially prolonged flight without visual reference, small errors could accumulate. The artificial horizon, a critical instrument during instrument flight, depended on internal gyros maintaining accurate orientation. If those systems degraded or drifted, the information presented to the pilots could become subtly misleading. Not obviously incorrect, just slightly off, enough to introduce doubt. Control feedback was another factor. The Viscount did not have modern fly-by-wire systems or advanced stability augmentation. Control forces were transmitted mechanically. If aerodynamic conditions changed, due to icing, turbulence, or airflow disruption, the feel of the aircraft could shift. Again, not dramatically, but noticeably. These were not failures. They were characteristics, and in isolation, they were manageable. Crew, training and interpretation. The flight crew operated within a system that emphasized discipline and procedural accuracy. They were trained to trust their instruments, particularly in conditions where external visual references were absent. Instrument flight was not optional. It was essential. At night, in cloud, it was the only reliable method of maintaining orientation. But training in this era had its boundaries. Instrument interpretation assumed that the instruments themselves were functioning correctly. Cross-checking between instruments was standard practice, but the range of available redundancy was limited compared to modern aircraft. When discrepancies arose, resolution depended on experience and judgment. There was no automated system to flag conflicting data, no alert to indicate unreliable readings. The pilots had to identify inconsistency themselves. Cockpit hierarchy also played a role. The captain's interpretation carried primary authority. The first officer supported, monitored, and assisted, but the decision-making process remained centralized. If uncertainty developed, it was resolved through that structure. In routine operations, this system functioned effectively. In ambiguous conditions, it could slow the recognition of subtle problems, not through error, but through design. Environment, the absence of reference. The environment on the night of the flight was not extreme. There were no severe thunderstorms, no violent turbulence, no conditions that would immediately signal danger. Instead, there was something more subtle: cloud layers, darkness, limited visual reference. At altitude, the aircraft entered a zone where the horizon was no longer visible. The ground, far below, offered no usable light. The sky, obscured by thin cloud, removed the stars as a reference point. This created a condition known in aviation as featureless visual environment. In such conditions, the human sensory system becomes unreliable. The inner ear, responsible for balance, can misinterpret motion. A gradual bank can feel like level flight. A descent can feel like stability. Without visual cues, perception detaches from reality. This is why instrument flying exists. It replaces sensation with measurement. But when instruments themselves become ambiguous, or when their interpretation becomes uncertain, the absence of external reference becomes critical. The pilots are left with no independent confirmation. Only data, only interpretation. Systems, information without certainty. The Viscount systems provided the crew with continuous data: altitude, airspeed, attitude, engine performance. Each parameter was displayed through analog instruments, clear, readable, and, under normal conditions, reliable. But these systems were not designed to handle every scenario with equal clarity. Gyroscopic instruments, for example, could be affected by prolonged uncorrected motion. If the aircraft entered a subtle but sustained deviation, the instruments could begin to reflect that deviation as normal. This is not a failure in the traditional sense. It is a limitation. The system assumes that deviations will be corrected quickly. When they are not, the baseline begins to shift. Cross-checking instruments could reveal inconsistencies, but only if the discrepancies were large enough to notice. In the early stages of a developing problem, those discrepancies might remain within acceptable margins, too small to trigger immediate concern, too significant to ignore indefinitely. This creates a narrow zone, a space where the aircraft is no longer behaving exactly as expected, but not yet clearly outside operational limits. It is within this space that decision-making becomes most difficult. The convergence. Individually, none of these elements guaranteed an accident. The aircraft was capable. The crew was trained. The environment was manageable. The systems were functional. But aviation safety depends not only on individual reliability. It depends on interaction. When aircraft behavior begins to shift, even slightly, the crew must detect it. When detection occurs, interpretation must be accurate. When interpretation is made, corrective action must be effective. If any part of this chain weakens, the margin for recovery narrows. On this flight, that chain began to stretch. The aircraft introduced subtle deviations. The environment removed external confirmation. The instrument provided data, but not certainty. The crew, operating within the structure of their training and tools, began to interpret a situation that was not fully clear. Not wrong, not yet, but no longer simple. The Viscount continued through the night, carrying within it a system under quiet strain. No alarms, no dramatic failures, only a gradual shift from stability toward uncertainty. And within that uncertainty, the conditions for loss of control were forming. The transition from uncertainty to loss of control is rarely abrupt. It unfolds in stages, each one small enough to manage, until the accumulation is no longer manageable at all. For the Vickers Viscount 720, that transition had already begun. At cruising altitude, the aircraft had entered a state of subtle instability. The oscillations, first barely perceptible, had developed into something more structured. Roll and pitch were no longer independent. They were interacting. The aircraft was beginning to diverge from controlled, steady flight. Inside the cockpit, the instruments continued to display data, but the relationship between those readings had started to shift. Indications no longer aligned as cleanly as they had minutes before. A slight bank registered, then a correction. But the correction did not fully resolve the deviation. Instead, it introduced a secondary motion. This is where control begins to degrade, not through absence, but through inconsistency. The pilot's increased input, still measured, still controlled, but now intentional. The aircraft responded, but unevenly. Roll rate increased beyond expectation. Pitch began to fluctuate more noticeably. Altitude, once steady, began a gradual but continuous decline. At this stage, the situation remained recoverable, but recovery required clarity, and clarity was becoming harder to maintain. The onset of disorientation. Without an external horizon, the crew relied entirely on instruments. But the instruments, affected by the developing motion, were no longer presenting a perfectly stable reference. The artificial horizon suggested one attitude. Other instruments, rate of tone, vertical speed, hinted at another. The discrepancies were not extreme, but they were enough. Enough to force interpretation rather than simple reaction. In aviation, this is a critical threshold. When pilots must decide which instrument to trust, time begins to compress. Every second spent interpreting is a second without effective correction. The aircraft continued to roll, not violently, but progressively. The bank angle increased. Corrective input followed, but the response lagged, or overcorrected. The motion became cyclical, each correction feeding into the next deviation. Escalation. The descent rate increased. What had been a slow loss of altitude became a defined downward trajectory. Engine power remained unchanged. There was no thrust loss. This was not an engine failure. It was a control problem. An aerodynamic divergence. The aircraft's nose dropped further. Airspeed began to rise. With increased speed came increased control sensitivity, but also increased structural loading. The Viscount was not designed for sustained high-speed descent in unstable attitudes. The margins were narrowing. Rapidly, loss of stable reference. At this point, the crew faced a condition known, though not yet formally defined in that era, as spatial disorientation. The human sensory system, deprived of visual cues, began to conflict with instrument data. A bank could feel level. A descent could feel stable. The body could no longer be trusted. Only instruments remained. But the instruments were no longer simple to interpret. This is the point where control is not lost instantly, but begins to slip. The aircraft entered a steeper bank. Control inputs increased in magnitude. The response became more aggressive, but not more effective. Instead of stabilizing, the aircraft began to oscillate more sharply. Roll led to pitch. Pitch fed into descent. Descent increased airspeed. Airspeed amplified every motion. The system was now feeding itself. The break point. There is always a moment, brief, often indistinct, where recovery transitioned from possible to improbable. For this flight, that moment occurred as the aircraft exceeded the limits of stable aerodynamic control. The bank angle became too great, the descent too steep, the speed too high. Control inputs, no matter how correct, could no longer fully counteract the aircraft's motion. The Viscount entered a descending spiral, not a vertical dive, not an uncontrolled tumble, but a tightening, accelerating spiral through cloud. The aircraft was still intact, the engine still operating, but controlled flight had been lost. Final descent. Altitude decreased rapidly. Cloud layers passed in quick succession. The aircraft remained enveloped. No visual recovery was possible. The descent rate increased further. Structural loads built as speed continued to rise. The aircraft's design limits were being approached and then exceeded. At high speed, even small control movements generate significant aerodynamic forces. In a spiral descent, those forces multiply. The Viscount, no longer stabilized, was subjected to stresses it was not designed to sustain in that configuration. The outcome, at this stage, was no longer dependent on a single action. The system had moved beyond correction. It was now governed by physics alone. Impact. The aircraft emerged from cloud too low for recovery. The descent trajectory remained steep. There was no time, no altitude, no remaining margin. The Viscount struck the ground at high speed. The impact occurred within seconds of exiting cloud, without a stabilized flight path, without controlled descent. The aircraft was destroyed on impact. There was no post-impact fire sequence that defined the event, no extended wreckage trail. The accident was sudden, final, complete, silence. The engines, which had maintained their steady rhythm throughout the flight, fell silent. The system that had functioned reliably across countless flights had reached its limit, not through a single failure, but through convergence of factors that, together, could not be resolved in time. What remained was absence. No transmission indicating distress. No clear signal of a specific malfunction. Only the knowledge, reconstructed later, that a routine flight had entered a condition from which recovery was no longer possible. In the hours following the disappearance of the Vickers Viscount 720, uncertainty replaced routine. The aircraft had not arrived. No distress call had been received. Radio contact, once steady, had simply ended. At first, the absence was procedural. Delays could occur. Communication gaps were not unheard of, particularly in areas where radio coverage depended on ground-based relays. But as time passed, the absence took on weight. The aircraft was declared overdue. Search procedures began. Search and location. The initial search effort relied on the last known position, an estimate based on radio communication and flight progress. Aircraft were dispatched along the expected route. Ground teams were mobilized in areas beneath that path. The terrain between Sydney and Melbourne is varied. Open land in some regions, forested and uneven in others. Locating wreckage without a precise position was a challenge. Hours turned into a full day, then longer. Eventually, wreckage was located in a remote area, confirming what had already become likely. The aircraft had impacted terrain at high speed. The debris field was relatively contained, consistent with a steep, uncontrolled descent rather than a shallow, extended breakup. There were no indications of in-flight explosion, no evidence of fire preceding impact. The aircraft had remained structurally intact until the final moments. This finding narrowed the possibilities, but it did not provide answers. The investigation begins. The responsibility for determining cause fell to Australian aviation authorities, supported by technical experts and representatives from a manufacturer. In the early 1960s, accident investigation operated under significant constraints. There were no cockpit voice recordings, no digital flight data, no recorded parameters tracking altitude, speed, or control inputs. The investigation would depend on wreckage analysis, maintenance records, weather data, operational procedures, known characteristics of the aircraft. Every fragment mattered. Every component was examined for signs of failure. Control surfaces were inspected to determine their positions at impact. Engines were analyzed to assess whether they had been producing power. Instruments, where recoverable, was studied for clues about the aircraft's state in the final seconds. Eliminating the obvious. The first phase of investigation focused on ruling out catastrophic causes. Engine failure was considered, but evidence indicated that all 4 engines were operating at the time of impact. There were no signs of mechanical disintegration, no blade separation, no internal damage consistent with pre-impact malfunction. Fire was examined. There was no indication of in-flight fire affecting structure or systems. Sabotage or external interference was not supported by any physical evidence. Structural failure was also investigated. While the aircraft had experienced high forces during descent, there was no conclusive evidence that structural breakup had initiated the event. This process of elimination was methodical. Each possibility was tested against available evidence. Each one, in turn, was reduced in likelihood. What remained was less definitive, a more complex picture. With major mechanical failures largely excluded, attention shifted toward operational and aerodynamic factors. The pattern of wreckage suggested a high-speed descent with significant vertical velocity. The lack of a long debris trail indicated that the aircraft had not broken apart at altitude. Instead, it had remained intact during a rapid, uncontrolled descent. This pointed toward loss of control. But loss of control requires a trigger. The investigation examined environmental conditions. Weather reports indicated cloud layers along the route. Visibility at altitude would have been limited. Night conditions further reduced external reference. This aligned with the possibility of instrument flight under degraded visual conditions. Attention then turned to the aircraft systems, particularly those that could influence attitude awareness. Gyroscopic instruments, if affected by prolonged or unusual motion, could provide misleading information, not incorrect in a dramatic sense, but offset, enough to create confusion. Without flight data recordings, however, this could not be proven conclusively. It could only be inferred. Human factors. The role of the crew was considered carefully and respectfully. There was no evidence of negligence, no indication of procedural disregard. The crew had operated within the standards of the time, but those standards had limitations. In conditions of reduced visibility, pilots depended entirely on their instruments. If those instruments became ambiguous, or if their interpretation became uncertain, the margin for maintaining control narrowed. The concept of spatial disorientation was known, but not fully understood in operational terms. Training addressed it, but mitigation tools were limited. There were no automated warnings for unusual attitudes, no systems to cross-check and flag conflicting instrument data. Recognition depended on the crew. Correction depended on timing. The investigation concluded that the aircraft likely entered a state where attitude awareness degraded, not suddenly, but progressively. And once that degradation reached a certain point, recovery became increasingly difficult. The findings, the final report did not identify a single definitive cause. Instead, it described a sequence. The aircraft entered cloud at night, removing external visual reference. A deviation from stable flight developed. Instrument interpretation became uncertain. Control inputs were made, but did not stabilize the aircraft. The aircraft entered a descending spiral. Recovery was not achieved before impact. This was not a conclusion built on certainty. It was built on probability, on the balance of available evidence, on what could be supported and what could not. In modern terms, it would be described as a loss of control in flight, influenced by environmental conditions and limitations in instrumentation and situational awareness. At the time, it remained a partially unresolved event. Impact on aviation. The absence of a single clear cause had its own effect. It highlighted a problem that could not be traced to a single failure, a problem that existed within the system itself. This led to a shift in focus. from individual components to interaction, from mechanical reliability to human-machine interface. Airlines, regulators, and manufacturers began to reconsider assumptions, particularly those involving instrument redundancy, attitude awareness, pilot workload in degraded conditions. The accident became part of a broader pattern, one that would only become fully understood in the years that followed. A pattern where aircraft remained mechanically sound, but control was lost. In the years following the loss of the Vickers Viscount 720, the absence of a single, definitive cause did not diminish the significance of the event. If anything, it deepened it. Aviation had encountered a type of accident that did not originate from a clear mechanical failure, nor from a single identifiable error. It emerged instead from interaction between aircraft behavior, environmental conditions, and human interpretation. That realization would take time to fully understand, but its influence began almost immediately. From certainty to complexity. Prior to accidents of this nature, aviation safety had often been approached through direct cause and effect. An engine failure could be traced. A structural flaw could be identified. A procedural error could be corrected. But this event did not conform to that model. The aircraft was functioning. The crew was qualified. The environment, while limiting, was not extreme. And yet, control had been lost. This forced a shift in perspective. Safety was no longer only about preventing failures. It was about understanding how systems behaved when nothing appeared to have failed completely. Advancements in instrumentation. One of the most significant areas of change involved cockpit instrumentation. Gyroscopic instruments, while reliable, were not immune to subtle errors, particularly in prolonged, uncorrected motion. The need for greater redundancy became clear. Aircraft designs began to incorporate multiple independent attitude indicators, improve cross-checking capability between instruments, more reliable gyroscopic systems with reduced drift. Over time, these developments evolved into modern electronic flight displays, systems capable of presenting integrated, continuously verified data. But the foundation of that evolution lay in earlier recognition that a single instrument, no matter how trusted, could not always provide certainty on its own. The emergence of flight recording. At the time of the accident, there were no cockpit voice recorders, no flight data recorders. Investigators were left to reconstruct events without direct evidence of what had occurred in the cockpit. This limitation became increasingly difficult to justify. In the years that followed, regulatory bodies around the world began to require recording devices on commercial aircraft. These systems transformed accident investigation. They provided objective records of flight parameters, insight into cockpit decision-making, precise timelines of developing events. Future investigations would no longer depend solely on inference. They would have data, understanding human factors. Perhaps the most profound change came in the understanding of human performance under stress. Spatial disorientation, once considered a known but limited risk, became a central focus of research. Studies revealed how easily the human sensory system could be misled in the absence of visual reference, how gradual deviations could go unnoticed, how conflicting instrument data could delay recognition. Training began to evolve. Pilots were taught not only how to fly by instruments, but how to manage ambiguity, how to recognize unreliable indications, how to prioritize certain instruments over others in specific conditions. This was the beginning of what would later become structured human factors training. Crew resource management. In parallel, cockpit dynamics began to change. The hierarchical model, where decisions were centralized and rarely challenged, was re-examined, not as a flaw, but as a limitation under certain conditions. Crew resource management, CRM, though not formalized immediately, began to take shape as a concept. It emphasized shared situational awareness, open communication, cross-verification of decisions. The goal was not to reduce authority, but to distribute awareness, to ensure that when ambiguity arose, it could be addressed collectively rather than individually. A broader pattern. As aviation progressed into the late 20th century, similar accidents were studied across different regions and aircraft types. A pattern emerged: aircraft that were mechanically sound, crews that were properly trained, flights that began routinely, and yet, under specific conditions, control was lost. This category, loss of control in flight, became one of the most studied areas in aviation safety, and the accident examined here became part of that broader understanding, not as an isolated event, but as an early example of a complex problem. Quiet influence. Unlike accidents defined by dramatic mechanical failure, this event did not produce a single visible lesson. There was no component to redesign, no procedure to eliminate entirely. Instead, it contributed to a gradual shift, a deeper awareness that aviation safety depended on more than reliability. It depended on clarity, on the ability of systems to communicate accurately, on the ability of humans to interpret that communication under pressure. Closure. Today, aircraft fly with layers of redundancy unimaginable in the early 1960s. Pilots operate with advanced displays, automated warnings, and continuous data monitoring. Flight recorders capture every second. Training addresses not only technical skill, but cognitive limitation. These developments did not emerge from a single moment. They were built over time, from many events, from many investigations, each one adding a piece. The flight that departed as routine did not return, but it did not disappear without consequence. Its legacy exists in the systems that followed, in the questions it raised, in the understanding it advanced, and in the quiet, ongoing effort to ensure that uncertainty, when it appears, is recognized early enough to be resolved. The sky, as always, remains unchanged, but the way it is navigated has been altered carefully, deliberately, by lessons learned from moments like this.